Here we go. Question number 1. This is not any book. How can you tell if a compound is ionic or covalent? Question number 2. What do you do differently to name a covalent compound compared to an ionic compound? And you may or may not remember this. Okay, and then you are going to list the 10 Greek prefixes. So take a moment and do that. Make sure you've checked with your partner. You might not remember everything. No, because they're ionic. They're just the names. We do suffixes and we do prefixes when it's covalent compounds. Okay. I'll tell your mom. No, I'm kidding. I don't even know what you're talking about. It's all good. I have no idea what you're talking about. It's all good. I wouldn't tell anyway. That would not be right. Okay. How do you tell if a compound is ionic or covalent? It's ionic if it has a metal. Okay, so you're looking for a metal, and then the other element, of course, has to be a non-metal. And if it's covalent, that's going to be non-metals only. What do you do differently when you are naming a covalent compound as opposed to the ones we just did, which were ionic? Yes. We do an ide for these ones as well, right? Sodium chloride. Yes. Yeah, we use the Greek prefixes to tell us the number of atoms. And let's see what we can remember of our 10 Greek prefixes, because it may have been a while. Okay. Some of them are pretty easy. One is mono. 2 is di. 3 is tri. Okay, like a tricycle. 4 is one that usually messes people up, so spend some time sticking it in your head. What's 4? Tetra. I was trying to convince period 1 that Tetris is called Tetris because all the shapes have 4 little blocks in them. But a lot of people hadn't played Tetris, so that did not help them at all. And then I tried to tell them that juice boxes are called Tetra Paks, and a juice box has 4 sides, but most didn't know what a Tetra Pak was, so that didn't help them either. So you just have to stuff that one in your brain. I don't know how to make it any easier. Penta. I suppose if you've raised fish, anybody raised tetras? Maybe you could imagine 4 fish, but nobody's raised fish either, so that doesn't help you. You just have to remember it. Number 6. Now, 6 and 7 people tend to mix them up because they both start with the letter H. Okay, they both start with the letter H. 6 is, what's a 6-sided figure? A hexagon, so 6 is hexa. What's a 7-sided figure? A heptagon. Again, 7 tends to be one of the ones that people tend to forget, so I'm going to put a little star beside these ones just to be like, you know, spend a little maybe extra time. This one is not septa, not. Septa, none of the prefixes start with the letter S, none of them, okay? Hexa, hopefully you won't forget, but it has an X in it like the letter 6. Yes, they both have the letter X. I don't know if that helps. What do we call an 8-legged sea creature? An octopus. So octa is 8. 9, sometimes people have problems with 9. It's almost like 10 to the negative 9. What's 10 to the negative 9? Mega, kilo, deci, centi, milli, micro, nano. But it's not nano. We have to take the na and the no and we have to swap them. It's nonna. Nonna. Okay? And then finally, dec. Because how many, what do we call 10 years, a period of 10 years? We call that a decade, okay? So deca. Okay, so you must commit these to memory. In grade 10, you may have had a list of them. No such luck this year. Memorize these. There will be a quiz on this tomorrow, and you will have to have memorized your prefixes, but if it doesn't go well, you can redo it on Friday or Monday, right? You can be like, okay, I'm just gonna try it tomorrow to get, you know, to get my brain working on that. I can try it again on Monday because then I'll have the whole weekend to remember it. You know what I mean? There are people who have no problem memorizing. God bless you. That's lovely for you, but I know for some people it takes a little longer. Don't worry about it. That's why we have 4 versions of every quiz, okay? All right. Now, would that it were this simple and that was it. There are a couple little things, they're not too bad, but the first one is mono. Mono is a little bit troublesome because we do not use it on the first word. Okay. However, we do use it on the second word. So for example, here's a compound that later in this class we are going to draw a Lewis structure for. CO. I have 1 C, I have 1 O. Normally, when we do these, we would write prefix and then the name of the element, first element, and then we would write prefix and the name of the second element. But because we have mono, do we write monocarbon? No, we do not. We just write carbon. And for the second element, we do use it on the second element. So because we have one of them rewrite, monoxide. So no mono on the first word, mono on the second word. Now, you might have noticed that I didn't actually write mono on the second word. I just wrote mon, yes? And that brings up our second slightly weird point, and that is that we drop the letters O and A before oxygen or oxide. So our first example, we would take mono oxide, and we would look at that O and we would say, I have an O, and it is before oxide. So do I get rid of it? Yes, I do. Okay. And hopefully that one looks a little weird, like monoxide. Ugh, it looks strange, yes? Now, people get a little excited about this. They see O and A and they think all vowels. Did I say drop all the vowels before oxygen and oxide? No, I did not. So what if I were to write trioxide? Do I drop the I? No, I keep it because it's not an O and it's not an A. People also get excited in the other way and they think, oh, I drop O and A before all vowels. Did I write drop O and A before all vowels? No, I wrote drop O and A before oxygen or oxide. So if I was to write, oh, I don't know, mono, whoops, monoiodide, yes. Would I drop the O? No, I would keep it. I only drop the O and the A before oxygen or oxide. So if I had to do pentaoxygen, not that I can think of a compound where that would actually exist, but let's pretend. Okay, pentaoxide, do I drop that A? Yes, I do. Okay, so drop O's and A's before oxygen or oxide. And the only other thing I can think of that people sometimes mess up on is the first word just keeps its name. Whereas the second word we end up with ide. So if we were just to, and I will come back down here in a moment, but if we bop up here, you remember how I said, okay, we write prefix first element, and then we write prefix second element. We should add on to that it's not just prefix first element, prefix second element, it's prefix second element, ide. So that's the general formula, is you have the prefix in the first element, prefix second element, ide, but here there would be no mono. If you want that all summarized in one little bit there, that would be how you would write your formula. Oh, why are you making noise? Is good? So that's tomorrow's quiz. So practice for that is on page 16. I think, in the green book. Okay, however, we still need to press on with Lewis structures, so we are going to do that. Just by way of review, you are going to tell me who, yes, of course. You're going to tell me who are the 4 elements that do not want, that break the octet rule. Tell your partner. We all know about hydrogen, hopefully. And who are the other 3? BE, B, and AL, B-ball. How many electrons does hydrogen need? 2. How many does beryllium need? 4. How many does boron need? 6. And don't get carried away and say aluminum needs 8, because otherwise it would not be an exception to the octet rule. It would just follow the octet rule. It also just needs 6. And if you remember, we talked about this being like B-ball. Ball is like one word, so they have the same number of electrons that they need. Okay. Número 2. What are the only 2 elements? What are the 2 elements that only ever form one bond? I'm hearing a lot of hydrogen. Hydrogen is correct. It is the other one that people always get wrong on quizzes and tests. They try to double bond it because they're like, ooh, I could double bond this. Excellent. Woohoo. It is fluorine. Only one bond ever. And now to your partner, I would like you to list the first 4 steps. Draw a Lewis structure. First of all, we're going to count. What do we count? The valence electrons. Yeah, we draw the skeleton structure. Step number 3. We add lone pairs until all atoms have what? A full shell, a full octet have 8 electrons. And I'm going to put except the exceptions. And who are the exceptions? Hydrogen and B-ball. Whoops. Why did I put an A? That doesn't go there. Okay. 4th what do? We count and check. We count the electrons in the structure and we check against the valence electrons. Okay. So let's do some double bonding today. All right? Triple bonding, double bonding. And we're going to start with a compound that was a little bit challenging for some people when we did it by just trying to cram atoms together last week. Okay? And that compound is CO. And you could tell me the name of that compound, because we just learned how to do that. Who is the name of that compound? Carbon monoxide. Yes, carbon monoxide. No mono on the first, but mono on the second. Yes? Yeah, VE is for valence electrons, sorry. So we're going to start by counting our valence electrons. And don't forget, the number of valence electrons is told to you by the group. Okay, so look for the group number, but if it's a teen, you subtract 10, okay? Or just get rid of the 1, okay? Carbon is in group 14, so it has 4 valence electrons. Oxygen is in group 16, so it has 6 valence electrons. 4 plus 6 is equal to 10 valence electrons. To our skeleton structure, we need to put an atom in the center, except that there's only 2 atoms, so there won't be any central atoms. So we can just put them beside each other, okay? So here's our skeleton structure. What is step number 3? Tell your partner. Everyone always forgets it. What do we add? Lone pairs of electrons until everyone has 8 electrons. So, does carbon need lone pairs? Right now, how many electrons does carbon have? It's got a line, so that means it has 2. Does it want 2? No, it wants 8. So how many pairs do we need? We need 3 pairs. 1, 2, 3. Oxygen. Does oxygen need lone pairs? Again, it's only got that 1 bond, and remember, a bond is always 2 electrons, so it only has 2, so it also needs 3 pairs. Basically, as long as you have either a bond or a lone pair on the top, on the bottom, and on each side, you will have a complete octet. Okay? Once we get into double bonds, it gets a little more complicated, but for now, this is good. Step 4, we're going to count and check. So we're going to count the electrons in this structure. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12, 14. Are these the same? No, obviously 14 and 10 are not the same. And we're going to talk in terms of pairs of electrons. How many pairs too many do we have? We have 2 pairs too many. And when we have too many electrons, we go to step 5. Okay, so anytime you have too many electrons, you go to step 5, because step 5 involves getting rid of those electrons. And step 5 says that we erase lone pairs. And specifically, we erase lone pairs from the central atom. Now you might say, Ms. Spence, there is no central atom. There's nobody in the middle, there's just one end and the other end. But we can ask ourselves, if circumstances were different, who would be more likely to be the central atom? Would it be carbon with its 4 valence electrons? Or would oxygen be more likely to be the central atom with its 6 valence electrons? Who is more likely to be central? Carbon, because it can form 4 bonds, whereas oxygen can only form 2 bonds. So carbon, we're going to call it the quote-unquote central atom, even though it's not really central. Okay, we're going to pretend like it's central. Technically, for this compound, it doesn't matter where you erase them from, but it's nice to have just have a dependable pattern to work with. Okay, so we're going to erase pairs from the central atom. And can you guess how many pairs we will erase? We are going to erase 2 pairs. And who are we going to erase them from? We are going to erase them from the central atom, or the one that would be central if there were a middle to be in. And so we're going to erase 2 pairs from carbon. So what that means is we can take this pair and this pair, and we can erase them. I'm going to redraw it, and you can just erase them. Okay, so now they're gone. Now, the nice thing about this particular method of doing this is that you know you've erased 2 pairs because you had 2 pairs too many. This also tells you the number of lone pairs you erase is going to tell you the number of multiple bonds you will form. So how many multiple bonds are we going to be forming? We had 2 pairs too many, so we erased 2 pairs, so we're going to form 2 multiple bonds. Now, how do these multiple bonds come to be? This is going to be step 6. Whoa, moving all over. There we go, that's better. In step 6, we move lone pairs. We turn lone pairs into bonding pairs. Until the central atom has 8 electrons. Guess how many lone pairs we turn into bonding pairs in this case? Super hard. We had 2 pairs of electrons too many, so we erased 2 pairs of electrons. So how many lone pairs are we going to turn into bonding pairs? 2. 2 lone pairs, I'm just going to call them LP, go to 2 BP, bonding pairs. Okay, so where are these lone pairs going to come from? We're going to take them from oxygen, because right now oxygen has enough. Okay, and we're going to say, oxygen, would you be so kind as to share these electrons with carbon? So that lone pair is going to cease being a lone pair and it will become a bonding pair. And we need to do this to 2 pairs, 2 lone pairs. So we're going to also take some electrons from the bottom here, and we're going to turn that lone pair into a bonding pair. And what that's going to look like is we will have carbon with the original single bond, but now we have a red bond that's a multiple bond, right? Now we have a multiple bond. We have one multiple bond, the red one. And we also have the green pair of electrons, which is our second multiple bond, right? So now we have 2 multiple bonds. We have 2 pairs of electrons that have turned into bonding electrons. By the way, if you cannot tell the difference between the top line and the bottom line, go get your eyes checked. You may be colorblind. I consider this a public service announcement because I have, in the course of my 27 years, taught at least 2 people who have discovered they were colorblind by taking chemistry, because we use a lot of colors. And I'm like, the green line and the red line. And he's like, I can't tell which line is which. And I'm like, you might want to get your vision checked. Not that there's much you can do about it, but it's good to know. They do have some new developments that are happening. Like there's some glasses you can get that can actually kind of compensate for it. It's kind of amazing. I don't know how well they work, but there's new developments happening all the time. Anyway, so we've now taken lone pairs, made bonding pairs. So now we have this bond here. What kind of a bond is that? It is a triple bond, which consists of a single bond and 2 multiple bonds. Or a sigma bond and 2 pi bonds, if you're like into that kind of thing, but that's okay. You're not. Never mind. Yes. Yes. Sigma pi pi. Why did I write triple bonds? It's just triple bond. We don't call it triple bonds. And we can check that, yes? No, it's okay. It would be weird though. It would be like saying Wesley's. Hello, Wesley's. How you doing? It'd be weird. Okay, we can check and we can say, do we have 8 electrons for carbon? Well, it's got a lone pair, that's 2, and then it has 3 bonding pairs, 4, 6, 8. Yay! And same thing for oxygen, it's got 2, and then it's got 4, 6, 8. And all together we have 2, 4, 6, 8, 10 electrons, which is the same as the number that we started with. Now all that's left is step number 7. Do you guys remember what step 7 was? Is it an ion? And if the answer is no, you're done. And the answer is no, it's just CO. There's no charge on it. It's not an ion. So we're done. We're going to do one more example, and then I'm going to let you practice a bit. HCO2 minus. Now this time I'm actually going to show you a different way of counting the valence electrons rather than right underneath, because some people tend to get a little confused. So sometimes it's nice to do it like this and say I have one H, I have one C, I have two O's, and I have a charge. This way you're not going to forget your H, your C, your O, or your charge. And sometimes people do forget those things. So this is going to be 1 times, this is going to be 1 times, this is going to be 2 times, and your charge is just going to be whatever your charge is. Hydrogen has 1 valence electron. Carbon has 4. Oxygen has 6. And then for our charge, remember, if the charge is negative, that means we added electrons. And since our charge is just negative, remember negative means -1. And so that means we added 1 electron when we are 1 negative. So we're going to have 1 electron here. This might seem like more work, but it does make sure that you don't make mistakes. So I have a 1 and a 4 and a 12 and a 1. And if I add those all together, I get 18 valence electrons. Yes, of course. So that's step 1. Of course, you can do it underneath if you don't lose track of them. That's totally fine. Step number 2 is our skeleton structure. And when we do our skeleton structure, we need to think, who is the central atom? And we might say, oh, it's usually the first one, first in the formula. Except that the first in the formula in this case is hydrogen. Is that okay to be in the center? No. So you can just go, okay, no. And we might say, okay, it's our singleton. Obviously, hydrogen is a singleton as well, but we've already eliminated that. So who is our singleton? Carbon. Is carbon okay? Yes. And here's like a little extra tip. If carbon is present, it is always central. Okay? So that would be another way of going about it. Because it's got those 4 unpaired electrons, it's always going to go in the middle. Okay, so number 1, we've said carbon is the singleton and carbon is always in the middle. So, hey, okay, so let's put carbon in the middle. And attached to it, how many atoms will be attached to it? There's going to be 1 hydrogen and 2 oxygens, right? 1 hydrogen, 2 oxygens. So there's going to be 1, 2, 3 things attached. Doesn't matter. Does it matter if I put it on the top and the sides or no? Okay, I'm just putting them here. So I have 1 hydrogen and I have 2 oxygens. Step number 3. Add lone pairs until we have 8 electrons. And we can go through each atom and we can say, does hydrogen need any lone pairs? No, because it already has 2, and hydrogen is one of the exceptions that only needs 2. How about carbon? Does carbon need any lone pairs? Yes. How many electrons does carbon have right now? It has 6, so it needs how many lone pairs? It needs 1 lone pair. I would never write this out. I would just draw the lone pairs on, but you know, it's kind of like the process, right? So here's our lone pair on carbon. How about oxygen? Does oxygen need lone pairs? Yes. How many electrons does an oxygen have? We just have that 1 bond there, so it's got 2 electrons, so it needs how many lone pairs? 3 lone pairs. And again, you could just say, oh, well, it's got 4 sides and it's only got things on one side, so I need to put something on the top, something on the side, and something on the bottom. Step number 4, we're going to count and check. So we have 2, 4, 6 in the bonds, 8, 10, 12, 14, 16, 18, 20. So I have now counted. Now I need to check. Is 20 the same as 18? Obviously, no. Okay, so I can like, there we go. Not the same. And then we ask ourselves, how many pairs too many? There's 1 pair too many. And if we have too many pairs, where do we go? We go to step 5. And what is step 5? Erase. And what are we erasing? Tell your partner, what are we erasing? Here's a clue. We have 1 pair too many, so we are going to erase lone pairs. Yes, okay, we're not going to erase bonding pairs because that would just blow our molecule apart. So we're going to erase lone pairs. And who are we erasing it from? From which atom? Bye. Central atom. Okay, so we're going to erase lone pairs from the central atom, and because we had 1 pair too many, we are going to erase 1 pair. So you can just go erase it. I'm going to redraw it. I'm taking it off of the carbon. Good thing there was only 1 pair to erase because the carbon only had 1 lone pair. And then step 6, we're turning something into something. We are turning lone pairs into bonding pairs. And we're always going to, if we erased one pair, we're going to turn one lone pair into a bonding pair. Where will we get this lone pair from? From anybody that is not the central atom, okay? And quite frankly, in this case, the central atom doesn't have any left. So we can choose either oxygen, we can choose whichever pair of electrons we want. I'm just going to grab these ones because why not? Okay, so we're going to take that pair and move it in between the oxygen and the carbon so it belongs to both of them rather than just oxygen. I am going to redraw this. Here I have carbon and I have oxygen. It still has 2 pairs of electrons. The red pair has moved here. Now, I could draw the electrons on the side and on the bottom. I like to draw them symmetrically on the 2 sides, but you don't have to. It would be okay if you drew it like this, right? Or like this. That would be okay, okay? And then finally, we just finish putting everything back where it was before, because the rest of it didn't change. You can check to see, does everybody have 8 electrons? Who needs it? Does carbon have 8 electrons? Yes, it has 4 bonds. It's got 4 lines, so that's 4 pairs. Does the oxygen on the right have 8 electrons? Yes, because it's got 3 lone pairs and a bonding pair. And how about the oxygen at the bottom? It has 2 lone pairs and 2 bonding pairs, gives us 4 pairs, gives us 8 electrons. Hooray! Everybody's good. Let's check the total number of electrons just to be sure. 2, 4, 6, 8, 10, 12, 14, 16, 18. And how many did we have? We had 18. Hooray! I know I didn't get all the way up to where it said 18. And the only thing I have to ask myself is question number 7, or step number 7. Is it an ion? Is it? I have to go back and look. Let's go see. Was it an ion? Oh, I went back too far. Ah! Where is it? There it is. HCO3 minus. So yes, it is. When it is an ion, what's the extra step I have to do? Brackets, what kind? Square or round? Square. And the charge, you can either write minus or -1, whatever you prefer. I like minus because that's the grown-up way of doing it. Okay, and there we are. We're done. Thank you for being so patient with such a long lesson. I've got to cram some stuff in before the weekend. Yeah, so homework, there's 2 things in the yellow book, page 124. We're going to do number 13, 14, and 16. And then in the green book, I think I already told you this page. I think it's 16. Yeah, page 16. So that's the quiz tomorrow. Okay, Friday there will be a quiz on Lewis structures. And I'm going to press stop recording so I don't end up with like hours at the end, which I often do. Stop.